Welcome to Ready to Derive. In this video, we're going to explore a rather interesting and what I consider fun application of derivatives, which is related rates. Now, it's not everyone's cup of tea, but I'm hoping that at the end of this video, you'll have the tools to be able to tackle these and maybe even find some enjoyment in related rates problems. So what kind of scenario might we be exploring? Well, imagine dropping a pebble into a pond. And we know that that will create ripples, and those ripples will expand with time. And in that scenario, there are actual rates that are related. It's some sort of interesting thing we could determine about those ripples. And a type of rate we might, if we were given, for example, dr by dt, the rate at which the radius is increasing, by the end of this video, we will be able to find a related rate, which is the rate at which the area of the circle or the ripple is increasing. So we're going to begin with a refresher on implicit differentiation because it's very important moving forward, and in particular we need to know how to take the derivative with respect to time. I will introduce a 4-step strategy to help solve related rates problems, and then besides exploring the ripple problem, we will look at a classic, the sliding ladder problem. This is only an introduction. We will treat more advanced scenarios in further videos. So without further ado, let's get started. Before we get into the nitty-gritties of related rates, it's important to do a little review of implicit differentiation. Now, the derivative, d by dx, is the operator, so that it says take the derivative of x squared, and we know from past experience that that's just 2x. That's pretty straightforward. But what happens when the variable, we want to take the derivative with respect to x of some other quantity squared, assuming that's dependent on x? Well, we know that it's really the chain rule that we're applying here. So the derivative of y squared is 2y, and then we have to multiply by the derivative of y itself with respect to x, because y is not explicitly expressed in terms of x. And so, and here's one that sometimes gets people a little confused. The derivative with respect to x of y, well, we can't actually do any, there's no real power rule to do here. You could say, all right, you could say that's a 1 in front of the y. So the derivative of 1y is 1. So sort of power rule times dy by dx, but that's just dy by dx. So whereas d by dx is an operator, it's instructions to do something, dy by dx we know is the notation used to represent the slope at a point on the curve. So now let's start introducing derivatives with respect to time, because that's how we're going to get at related rates. So by the same reasoning, the chain rule, the derivative of x squared is 2x, but we can't stop there because now these variables don't match. So we have to do 2x, the derivative of the outer function, times the derivative of x with respect to time. And that, of course, will be the same for the derivative with respect to time of y squared. So it would be 2y dy by dt. And then now here's an interesting one, because the derivative with respect to time of x, now x doesn't get sort of any privileged status now because the variables, once again, don't match. It's not with respect to x, the derivative. So d by dt of x is just dx by dt. And yes, while that is slope, it's also moving forward, we're going to think of this as the rate at which the quantity x is changing. So we'll have a little more practice finding the derivatives with respect to time. This time we'll do some operations with the variables x and y and just make sure we can accommodate that. So we would like d by dt of x squared plus y squared. Remember, the assumption here is that x and y are both quantities that are varying with respect to time. So x could be the side of one square, and x squared would be its area. Y, the side of another square, y squared, its area. So we might be interested in how the total area is changing with respect to time. So to do this, we just take the derivative of x squared with respect to time, as we did in the previous slide, and y squared, and just add them together. But what if we multiply x squared and y squared? And we have to realize that we do actually have a product here, so we have to apply the product rule. So the derivative with respect to time. So the derivative of the first quantity, x squared, would be 2x dx by dt. But don't forget to multiply it by the other component, y squared, and vice versa, 2y dy by dt. This should be kind of second nature now, but good to have the specific practice. So the derivative with respect to t of x plus y, as we saw in the previous slide, that's just going to be dx by dt plus dy by dt. And remember, we are understanding that something like dx by dt is actually, while it does represent a slope with respect to time, it really boils down to finding the rate of change of x. And dy by dt would be the rate of change of y. Now, what about if we have a situation here where we have the quotient rule that we have to apply now? So quotient rule. So let's get all the components straight. So the derivative of the numerator would be just dx by dt times the quantity in the denominator minus, and vice versa, x dy by dt all over y squared. So now that we are pros at finding derivative with respect to time, we're going to apply this to some familiar equations. So here's the Pythagorean theorem. And if we take the derivative with respect to time of both sides, we know we will get 2a dA by dt plus 2b dB by dt equals 2c dc by dt. And we see that if we know how, say, the legs of a right triangle were changing with respect to time, we could use this formula to find how the hypotenuse is changing, if providing we have the values of a, b, and c. Okay, so let's do the derivative with respect to time of the area of a triangle formula. So dA by dt would be a half, and then I'm realizing that b times h, both dependent on time, we assume, then we're going to have to use the product rule. So it will be dB by dt times h plus b times dh by dt. And here's the perimeter of a rectangle. So dp by dt, the rate at which the perimeter is changing, will be 2 times the rate at which the length is changing, plus 2 times the rate at which the width is changing. It sort of makes sense because of that linear relationship. And finally, what about this situation? So the derivative of tan theta would be secant squared theta, but we mustn't forget to multiply by the derivative of theta with respect to time. And with that 1/5, think of it, rather than use the quotient rule, since 5 is a constant, it's better to think of it as just 1/5 times h. The derivative of h with respect to time is just this. So this might be a situation where we want to find how the angle of a triangle, a right triangle, is changing given the rate at which its height is changing. So now we have the tools needed to be able to tackle a related rate problem. We're going to revisit the scenario from the opening slide. So we're dropping a pebble from a bridge into a pond. There's the pebble, and that causes a ripple to start moving outwards. Okay, so we're just following the trajectory of the ripple there. And we are told, we can't work out related rates unless we're given one or more rates. So we've given the rate at which the radius is increasing is 3 inches per second. And we'd like to find out the rate at which the area of the ripple is increasing when its radius is 1 inch, 2 inch, and 3 inches. So what we do first is let's just put that 3 inches per second, let's put that into mathematical notation. That rate represents dr by dt. And the rate we would like to find, we know we can write as dA by dt. So what do we do next? We find an equation relating A and R. A, the area of the circle, with the radius, and we know that is A equals pi r squared. And we do what we've been practicing, which is we find the derivative with respect to time, both sides of this. So we get dA by dt equals 2 pi r times dr by dt. We have created an equation in which the rates are related. Now, I like this equation. It's kind of cool because this is 2 pi r is the circumference of a circle. If we think about how a circle might grow, so here's maybe a ripple. So we're looking head on at the ripple now, whereas the picture before, we were trying to show the ripple at an angle to the surface of the pond. But it sort of makes sense that to grow a circle, so as a ripple grows, what you're really doing is think of it as you're just adding on a circumference. Every time you grow a circle, you're adding on a circumference. And the bigger the radius of the circle, the bigger the circumference. So that's kind of, let me take that away from there now, but that's why I like this formula. It seems to make logical sense with that 2 pi r being there. So now we get to use the formula for the various radiuses, and we can see that whereas the rate at which the radius is increasing is a constant, it seems like the rate at which it increases does indeed depend on r. So let's get this information in here. So we know when the radius is 1, we would just plug in r equals 1 into this expression, and we would get 6 pi, which is, just to make sense of it, is turn that into a decimal, rounds to 18.8, and the units inches squared per second, because we're talking about rate of change of area. And now if we put in 2 here, we would get 12 pi. So, it seems like the rate of change of the area is doubling, because if you think about it, you've got a much bigger circumference to add on to a circle that has twice the radius. And here we go for the last one. If we put a 3 in there, we would get 18 pi, and that comes out to be approximately 56.5 inches squared per second. So we have completed our first related rates problem. So let's look at a strategy for solving related rates problems step by step. This would be a good slide in which to take notes so you have them for examples moving forward. And we're going to just revisit the problem from before, but summarize it with the steps. So the first thing is to draw a diagram and assign a variable to each quantity that varies with time. So in the example of the ripple problem, we know that one variable was the radius, because we were given information about that. And we also know that the other variable of interest was the area. So A and R. So only 2 variables in this one. Let me just get rid of that, sorry. And in future ones, there could be 3 variables. There's usually at least 2 variables that you have to assign. And then the next step is that for each variable, you identify its rate of change. One is unknown, of course, and any snapshot value. So let me explain what I mean by that. So we were given, so dr by dt, that's one rate of change. We were given that was 3. And we know that dA by dt was what we were seeking, so that's unknown. Now the snapshot values, as we saw before, you have to pick a radius at which to calculate the rate of change of the area. So just for contrast, we could say, let's say our snapshot value, we didn't do this in the table, we only went up to 3, but let's say we were interested when r equals 5. Now A also has a snapshot value at that time. When the radius is 5, obviously we could calculate the area, but we may not need that snapshot value, so we'll wait on that to see if it shows up in the equation. What equation? Well, that's the next step. You must write an equation linking all the variables and then implicitly differentiate it. So we only have 2 variables, and we know that the equation linking them is A equals pi r squared. And then we did implicit differentiation, and we got this 2 pi r times dr by dt. So that's step 3. And then the final step, only in the final step do you actually plug in the values you know and any snapshot values. So to find dA by dt for when it's 5, so 2 pi, the radius was 5, and dr by dt is 3. So that leaves us with 30 pi inches squared per second. And that's our final answer. So notice that we didn't actually need the snapshot value for A, this one up here, but you will find in other related rates problems that you might have to find other values at that moment in time when you want to work out the particular rate. So we're going to end with one more related rates practice problem. We'll certainly tackle others in later videos, but for this video, this should be sufficient. So a 10-foot ladder is leaning against a wall. The base of the ladder slides horizontally away from the wall at 3 feet per second. And this is a classic related rates problem. You just hope that you're not standing on this ladder. And as a result, the top of the ladder slides down the wall. So at what rate is the top of the ladder sliding down the wall when the base is 8 feet from the wall? So the first thing that we know we do is we make a diagram and we assign variables. So here we have, there's the floor and the wall, there is the ladder, and the ladder is 10 feet long. And now we need to assign, we know that the bottom of the ladder is sliding out and the top of the ladder is sliding down. So those are the quantities that are actually varying. So we should give a variable we call x, the distance of the base of the ladder from the wall, and let's call y the height of the ladder up against the wall. So our next step is to identify the rates of change / snapshot values of the variables. So all we know is that, let's see, dx by dt, that is the rate at which the bottom of the ladder slides horizontally. So dx by dt is 3, so we know that this is increasing as the ladder slides out. And we want to know about a rate when the base is 8 feet from the wall. So we want to know at the particular time that x equals 8. What do we want to know? Well, we want to know how y is changing. So we are looking for dy by dt. And the snapshot value, well, we don't know it, but we may need it. So we'll sort of keep our eye out for that. So these are the snapshot values that we're interested in. So x equals 8 and y equals, well, to be determined. So we'll do steps 3 and 4 on the next slide. So continuing practice problem 3, here is the diagram from before. Here are our rates and snapshot values listed for the time being anyway. And the next step we know is to write an equation linking the variables. So we've got the Pythagorean theorem going on here. So we know it must be x squared plus y squared equals 10 squared or 100. And then we take the derivative with respect to time. So this should feel very familiar now. 2x dx by dt plus 2y dy by dt. Now be careful here, the derivative of 10 squared or 100 is just 0, so that's gone. And while we're at it, we could also obviously we could divide through by 2, so we could cross those out. Might make the math a little easier. And then the last step is to substitute and solve. So we know that x, let's see, when we are interested when x is 8, and we know that dx by dt is 3. And here we go. It seems like we need to know what y is. So dy by dt is unknown. We want to find that, but we cannot solve this equation unless we find the value of y, the snapshot value. So that's what we're going to do now. For snapshot values, it's best to just redraw the diagram with the particular values in. So we have 8, 10, this looks like a familiar triangle. We can do the Pythagorean theorem, y squared plus 8 squared equals 10 squared, but it will turn out that y is 6, because this is a 3, 4, 5 triangle, 6, 8, 10. So y is 6, we get to put that value back in here, and then we get to solve. So dy by dt is equal to 8 times 3 is 24. Bring that to the other side. We get negative 24 divided by 6. And that comes out to be negative 4. And the units are feet per second. So that's our answer. And you should think for a moment about why is it negative 4. Why is it negative as opposed to positive? And that's because the top of the ladder is dropping down the wall, which means that y is decreasing in value. So therefore, the rate is negative. And that brings us to the end of this lesson. I hope you found it helpful. And if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.